do? It's
Yep.
out of 100, but you can get a 110 on it, right?
Yeah, in fact, I listed as maximum of 110, but it's scored as if it's out of 100, so the 10 points are extra credit. The 10 points, if you end up getting 100, it's 100.
Okay.
It's not 10 11s. So it gives you an opportunity. One part of the extra credit is relatively easy if you understand what we discussed in class. The other is a little bit more difficult. I'm so hoping a lot of people will do the first part with the thing where you add a column. I don't expect as many people to do the thing where you drop a column. But it's up to individuals, it's giving people an opportunity to do more. That's not that hard to do, it just requires a little more stuff we didn't go over in class.
Go on all the different
Let's not talk about it. Number one and number two, the assignment explicitly says you shouldn't go through all the records. Either for Ed or for drop.
Okay, you can do a three-dimensional one.
If you do all the records,
No,
it's
sorry,
not,
two.
it's not what's
A
desired.
two-dimensional.
Okay, well, we're actually hitting 10:40 right now, so why don't we get into it, and we'll see. And for some reason, I think it has to do with buses. People have a tendency to come into the class a little bit late, but imagine what it would be like if the class had been when it was originally scheduled, which was 8 a.m. yawn. And I live in Los Altos, so I have to remember. I did that one quarter in one class and decided, bad mistake, let's try to avoid it in the future. Which I barely managed to do this time. Anyway, you know about Project 2, it's due by next Thursday, so please keep attending the lab sections to ask about it. We've already talked about what's involved in doing it. You can use our Project 1 solution, or you can do it using your own. The Project 1 scores have been unmuted, so you recognize that if you're using our Project 1 solution, the Project 1 tests are going to be run on Project 2. So you'll be inheriting your bugs in Project 1 for Project 2, which you probably don't want to have to do. The RBFM tests you may have noticed, and PFM tests are part of Project 2. You know about forwarding addresses and how to be able to deal with them. I urge people to read the report.txt for Project 2 because those are questions that you're going to have to answer, and so your solution should, try to deal with the issues that are mentioned there. If you have questions about your Project 1 scores, please ask about Project 1 no later than next Tuesday. So you can ask Saloni about your score today in the lab, you can ask her Tuesday in the lab, or you can just send her an email. The questions don't have to be resolved by next Tuesday, they just have to be asked. We're not going to have indefinite questions being asked. Everybody on the team should have the same score. For this lab, I think there are comments that are out there for everybody on the team. There may be more detail on the submitter, but I actually think it's the same comments out there pretty much for everybody. And, again, a week from Monday, there's an exam. We're about halfway through the term. This is the end of week 4, so that'll be the first day of week 6. No makeups, no early, no late, no devices, the usual thing. You can bring in the usual cheat sheet that you could do in 180, but of course no cheating and no sharing, although you can prepare the things together. You'll hand in the midterm, which you'll be doing on the midterm, so you don't have to bring any funny kind of Scantron sheets for the midterm. You'll be answering the midterm on the midterm. You should have plenty of space on that to be able to do it, so you don't need any scrap paper or whatever. But you'll hand in your midterm and your cheat sheet with your name on it on the top right, and of course you'll have to show your ID at the end of the exam. Last year's midterm was posted under resource exams, and the solution to that will be posted next week, so you'll have a chance to be able to look at that. But as usual, I urge everybody to go ahead and take the exam rather than just read the answers. We haven't gone over everything that's on the exam, but we've gone over a fair part of it. And again, I'll emphasize the first slide always tells you approximately what we're going over, except for the codas that I throw in. So you know what you can know in advance what we're going over and read it in advance or after class. So as I said, probably not during class, but that's your choice too. Where are we now? We're going from the bottom up, and we're going to be talking about optimization, and how you execute the relational operators. So we're going to be looking at how you can actually execute relational operators, and then we'll see how that goes into execution of entire queries and optimization, which is finding a good way to be able to execute the queries. As we talked about before, there are these different levels that exist in the system. There are open source parsers that are out there. Actually, somebody recently asked me about how they can parse SQL. Amazingly enough, this amused me. I hadn't known this. Uber has done a lot of work on open source parsing of SQL. I'm amused. I wouldn't have expected Uber to have open source that. But there are lots of parsers that are out there that you can understand. And the idea of parsing is to understand what the heck the query is talking about, and there's information inside your catalogs, the system tables, that tell you about aspects of the tables, what columns there are in them. So it tells you whether or not there's a legal column or an illegal column in your query, and what the types of the queries are, and what the lengths of the queries are, and all that sort of stuff. It also helps you understand what indexes and other access paths there may be for executing it. And then the query optimizer is going to say, hey, I can find a couple of different ways of executing this query. I can change the subquery into a join, or I don't have to bother doing distinct because it's going to be distinct anyway. And so there are lots of things that are done in this transformation part of the optimizer. And then there's cost-based optimizer, or sometimes rule-based optimizers, which try to find a good way of executing a query. Something I will emphasize, the term optimizer suggests you're finding the best plan. What the heck does best mean? Because you're not going to look at the data when you're trying to figure out what the right way of executing the query is. I suppose you could try to execute the query using every possible plan on the data that you have to find the best plan. That's really not a good idea when you're trying to actually execute the query. So the notion of what optimum means doesn't entirely make sense, because you have imprecise statistics about the tables that you have. You have cost estimates that, as we'll see, aren't strictly going to end up being right. You're not going to look at all the data to be able to find the plan. What you really want to be able to do when optimization started was avoid really bad plans, which could be an order of magnitude or two worse, and we'll see some examples of this compared to the better plans. And these days, plans can be really good. Plans can take advantage of all sorts of details. So just as I've emphasized all through the course, we'll talk about ways of doing this, but these days all sorts of interesting other ways get done. For example, and I'll mention pointer to such a paper later on in the course, there are learning optimizers, meaning that rather than just go ahead and say, well, we'll figure out what the cost should be, we'll go ahead and we'll say, hey, we're going to figure out what sort of plans end up working well and try to take advantage of them in the future when we have things that involve parameters that have certain shapes and statistics that have certain distributions and so on. So there's a lot of stuff that can be done and is done these days to be able to figure things out. Remember also, you don't want to be Hamlet. You don't want to spend all your time thinking about what the right thing is to do rather than do it. So basically, you find the really best way of doing things. The best way of doing things only takes 100 milliseconds, and you spend 2 seconds figuring that out. Maybe not the best choice of trade-offs, to execute or to execute. That's not a question. You really want to be able to execute your queries and do it in a reasonable time. So the good plan is going to be based on looking at the actual physical stuff. Remember, the physical representation of the data is encapsulated. You don't know what that physical representation is, but the optimizer does, the database system does, and it really will care about whether it's row form or column form or how partitioned the data is, all sorts of other execution related things that are there. It'll care about the access paths available, the statistics to the extent they're known, and there will be a cost model that gets used. So what we're going to do is we're going to start looking at this and looking at different ways you can execute different relational algebra operators. And I told you when we talked about relational algebra in 180 that to some extent it's not 100% true. An execution plan is like going ahead and mapping the declarative SQL query into something that actually does things involving using relational operators in some order. It's actually more complicated than that, but it's an approximation. So the idea is that you've got operators that you want to do, which can be things like select, project, and join, and also union and other operators that you're doing. And there'll be lots of ways that you can do this, and you can take advantage of access paths that let you, for example, be able to figure out, I only get the things that satisfy this predicate. If my query only wants the employees that have salary greater than 10,000, and I've got an index on salary, I can just look at the relevant employees whose salary is greater than 10,000 and not bother looking at the irrelevant ones. Although sometimes a file scan can be a faster way, even when there are relevant predicates that help you reduce what's involved. So we're going to be looking at tree of operators where, again, the general idea is that the next nodes higher up on the tree are going to ask nodes lower down on the tree to send them tuples. Now remember, you can think about this as a pull model or a push model. You can start executing things lower down and maybe store the tuples and then send them up when they're needed. But you don't want to push tuples up and overload somebody so that they end up spending so much time dealing with what you're sending them that they can't do their operation. So you could calculate things when they're needed, you can calculate a bunch of things and store them and send them up when they're needed. You can also send up a batch of things, so you might not want to send 1,000,000 things up to the next node, but you might go ahead and send 100 or 1,000 things up to the next node, and then when it wants to get next, it'll already have that number available. But you want to do flow control. You send everything up, and things are so busy dealing with what you sent that they can't actually end up doing work. So there are a lot of details of that, which are only partially discussed inside the book as you look at things at next level and pulling things up as you go. Yeah.
So which way is the pull model? Which way is the push model?
Basically, the graph is the same. The only question is, do you send things before they're asked for or only when they're asked for? So in the pull model, you send things logically only when they're asked for. In the push model, you're pushing things up as you get them. And the thing is that you really want to probably have something which is hybrid, where you might send more than one so that things are ready the next time that the next node up, in the flow wants it. But you don't want to send so many that it's drowning in stuff. So you might send, say, in my example, 100 up, so that it has 100 available, and then as time goes by, it might ask for, send me some more things. It's okay, I've used up half or 90% of what's there. Send them some more, so I won't have to ask you the next time. I'll have them ready. So in the push model, as you get things, you send them up. In the push-pull model, when you want things, you want them. In the hybrid thing that I described, you make sure that there's enough so you don't have to wait to get it, but not so much that you end up drowning in data.
Okay, awesome, thank you so much.
Yep, keep asking the questions. Okay, so some techniques, we mentioned this last time, that you can use are taking advantage of indexes so that you don't have to send irrelevant things to be dealt with. You end up only dealing with things that are, that are relevant. Iteration, where sometimes you want to be able to scan through everything inside a file, even though you might have some predicates, but sometimes scanning the data entries can be faster than using the index. And splitting things into pieces, both in how you store data, which we'll get to later on in the course, but also how you execute these operators, that can be an advantage. And often, by the way, in this class in general, the book calls it partitioning. Over the last 10, 15 years, and the book was written 15 years ago, 17 years ago, the term sharding has often been used instead of partitioning. It means the same thing. It's splitting into pieces based on some criterion, like ranges, or just randomly splitting into approximately equal pieces. You know why the word sharding has been used instead of partitioning? So that you don't get confused with the term partitioning meaning a network partition. Where you basically have a split brain where part of the network can't split to another part of the network. So variations of these will come. So when I say sharding, partitioning, in this course we're not going to be talking about network partitioning. They're synonyms. Okay, examples. Just like you got sick of movies in the 180 course, you're going to get sick of sailors and reserves and stuff. Maybe even sicker. It's going to be using this a lot all through the course. So, now you're being introduced to it, get used to it, but you'll get sick of it. I know I have. Anyway, in the sailors table, you're going to have the sailor ID, which is an integer, that's the key, You also have the sailor name, the rating, which is an integer, the age, which is real. We actually used a variation of this example for some things and with the group by in 180. And you have reservations, which we'll just abbreviate and call reserves, but it means a reservation. And what's going on is sailors reserve boats on days, and you have a name, basically a tag that's associated with the reservation. So, maybe could have called that a tag rather than a name, just some kind of code that you get for the reservation. And the key of that is SID, BID, and date, which says this sailor reserved this boat on this date. Sailors might have reserved multiple boats on the same date. Sailors might have reserved the same boat on several different dates. Several different sailors could have reserved the same boat, blah, blah, blah. So the key is a compound key of SID and BID and this day field, which is the date. So we've got the Santa Cruz Sea Slug Sailing Club, and I don't know if there really is one, but there could be. And inside that, in these examples, and the numbers are relatively small, but we'll have fun with it anyway. We'll have 40K rows, 40,000 tuples. Each tuple is going to be 50 bytes long, and if I divide, basically if I have 4K byte pages or 4,096 byte pages, we're going to simplify. We're going to have 80 tuples per page, which is basically just using 4K. 4,000 divided by 50 bytes means we can fit 80 tuples on a page. Okay, we might deal with 81, but I'm going to make the math simpler for us and just round off to hundreds, right? So it's sloppy, but it does make the math a little bit easier. And so, how many pages are there? There are 80 tuples per page. There are 40K tuples, so that means that there are 500 pages total. The math on that is pretty straightforward, right? 4,000 divided by 50 is 80 tuples per page, and 40,000 divided by 80 means that there are 500 pages total. Get used to this arithmetic. We're going to be using it a lot. Same thing on the members' reservations for the sailboats. We're going to have 100,000 tuples in that case. We'll assume each one of them is 40 bytes long. Since they're 40 bytes long and we have 4K byte pages, there can be 1,000 tuples that fit on a page, 40 times 100. That'll give us the 4K. And there are going to be 1,000 pages total because there are 100K tuples and there are 100 tuples per page. And so we're, in this case, assuming no free space. Yeah, I could have put in my calculation for free space, 10% free. Just makes the math a little bit more complicated. But in practice, yeah, you'd have to think about that. We're just making the numbers easier. And you'll have fun with the numbers as is, so be happy that I made the numbers easier. But, there are lots of more precise things you can do here. But we're simplifying. So used to the idea of what's going to go on here. We're going to come back to this slide. If I had two projectors, I would put this up on a separate slide, but we'll bounce back to this one, which is slide 7, periodically when we end up needing it, so get used to the idea. Okay, access paths, okay? An access path is what else? It's a path that allows you to access tuples. Good name, access path. So you can always, even if you don't have any other access paths, you can always scan the file. And in our examples, we'll have a file containing just a single table. In practice, you might have a file that contains, multiple tables. So you might have the departments table with the employees in that department interspersed with the departments they're in. But we're going to simplify and just have a single table/relation inside a file, as you have in the projects. And you can always access using the file scan, going through all the tuples in the file. If you split a table up, by the way, into 12 pieces, so I partition or shard it into 12 pieces, I could scan each of the pieces, or I could use indexes on some and scans on others. But I can also take advantage of my access paths like indexes that allow me only to find the things that match part of the index. So what does matching mean? Well, let's talk about a tree index and about a hash index, and we've already touched some of this. A tree index can match a condition, which is a conjunction. That is, conjunction just means ending together. It's an ending together of terms. When the tree index, when the condition only involves attributes that are in a prefix of the search key. That's a lot of words, but it'll be a lot easier to understand with an example. So suppose I have a B-tree index on ABC. I can use that to deal with the predicate A equals 5 and B equals 3. Because AB is a prefix of it, so I can only use the index to get the things that have that first, the major fields of the index, A and B, and only get the things with A being 5 and B equal 3. I can also use it for A equals 5 and B greater than 6. Because what I can do is use my B tree to find the things with 5 and then 6 within that, and only go forward with a B greater than 6, A equals 5 and B greater than 6, and that's okay. Okay? But it's not gonna be a match for B equals 3. I could use the index, it gets a little ugly probably, because I have to check all the A values, since A is the major field, to be able to find the things with B equals 3. It's not that I can't use the index, it's that unless there's a very small number of things in A, I wouldn't want to. So in general, assuming that there's a lot of things in A, B equals 3 would be a problem. What about a predicate where I have A greater than 5? Yeah, that would work. What about B greater than 5? Same deal. I'd have to try all the A values for the B greater than 5. What about A equals 5, B greater than 3, C, greater than 17? I can kind of use that because I can go ahead and have the A equals 5 and the B greater than 3. But then I can use it, but I'd have to check a bunch of irrelevant C values. So there's matching exactly, and there's things where you have, not perfect value. So if you have A equals 5, B greater than 3, C greater than 17, you can match it perfectly on the A equals 5 and the B greater than 3. The C greater than 17, you will be looking at the index only at certain things that are irrelevant, because C is the minor field within B. Question?
Could you do like A greater than B or B greater than A?
What do you think?
Yes.
It would be something where you could check it out using the index, but it gets awkward. In other words, there's irrelevant on the index and there's irrelevant on the data. You avoid looking at anything irrelevant on the data if you have, say, A equals B or A greater than B.
Mm-hmm.
But you end up looking at a bunch of irrelevant stuff inside the index. And so you have to look at the costs involved in doing that. So there's usable, and there's having, meaning you avoid irrelevance on the data, and there's really good match, which means you also avoid irrelevance in the index. And there's a cost, and there are trade-offs. So, all that is there. So again, B equals 3, I can use the index to avoid irrelevant data. But it's not going to be an exact match in the index because I'll have to check all the A's, and so I'll be looking at irrelevant things involving, I'll have to go through all the different A's, and for some of the A's there would be a B equals 3. For some of the A's there might not be a B equals 3, but I'll have to check out a whole bunch of stuff. So scanning the index is itself something which has a cost. And then there's hashing. Hashing is wonderful, marvelous, terrific, but only for equality, subject to the same caveat that I've already given you. So the match, if I have a conjunction of terms, is going to work if I have attribute equals value for every single attribute that I have in the hash index, every single one, not a prefix. It's got to be every single one, because the hash index allows me to find exact matches. It's not good on ranges. So if I have a hash index on ABC, it'll match A equals 5, B equals 3, and C equals 5. But it won't match B equals 3. And it won't match A equals 5 and B equals 3. And it won't match A greater than 5 and B equals 3 and C equals 5. Now, could I use, let's take the last one. Suppose I have a hash index. Could I use it? Yeah, I could try every single A value that was greater than 5. And if I know that the value of A is, less than or equal to 8, I could just try 6, 7, 8, and I could do it. So there's a question of, can I use it at all, and is it going to be, easy to use, and how much value does it have? So this notion of matching it's more than just matching. Again, if I know what the range of values is exactly, then I can go ahead and do it. But maybe I don't know what all the different values of A is. Maybe I knew it as of an hour ago, but new tuples have been put in that have other values of A. So you have to be careful about how that works. Fortunately, with a tree index, I can figure out what the values are pretty easily. But with a hash index, I can't. On the other hand, I'm keeping track of the low and high value as I go, or keeping track of some bit vector that tells me about the values. There are things that I can do. So take the caveat that there's whether or not you have a match that allows you to really get exactly what you want, or whether or not you can play games by using the hash index. I can always go ahead and search the entire hash index for things, and then only touch relevant data, but that gets expensive, depending on what the ranges are. And I've already given you the example. If I'm looking for salaries that are more than 10,001 cent, okay, 10,001 cent, 10,002 cents, 10,000, no, not something I want to do. Or if I have timestamps, then I'm looking for things that are later than a given date, too many different dates. I'm not going to use a hash index for that. The tree could be good, but you get the idea. So there's the notion of matching, and there's usability and avoiding irrelevance at several different levels. So let's take a look at this other predicate. I was talking about conjunction. The focus in System R and the focus in the textbook are avoiding disjunction. Conjunction means anding, disjunction means oring. And of course, we're dealing with a C club, so there's a lot of oring that's going on. Never mind. The bad jokes will not be on the exam. It's not too many of them. Anyway, if you have a predicate like this, you can also, you have to optimize it too, but our focus is not going to be talking about that. We'll be assuming that, the selection, this is what System R did, that everything gets mapped into C and F, which involves an anding together of ors. That's what C and F is, as opposed to D and F, which is oring together of ands. Okay, so the example of that would be, here's something which is in C and F, date less than that, or BID equals that, or etc. And that's an example of a C and F, and anding together of ors. We won't be emphasizing ors in this class. Let me just say a word about them, because it's really not fair to or, because they really do show up. But basically, you can optimize involving ors. It just means taking something where you take the unions of things, right? And it's a union without duplicates, because if something satisfies date less than 8994, and it also satisfies BID equals 5, and it also satisfies SID equals 3, you have a row that satisfies all three of those. You don't repeat the row 3 times. It satisfies the or, and it satisfies it once. And ors do get optimized, and it's just not the stuff that we emphasize in the lectures. There's a little bit about it in the text. Again, I'll be happy to talk with people more about it if you want to offline. So here's an approach to dealing with selection. You basically could try to go ahead and find the most selective access path if you're trying to access a table. The one that cuts down as much as possible, the one that avoids irrelevant stuff as much as possible. So you have a predicate that involves anding together several different things. You find the access path that gets rid of the things that you don't want as much as possible, and then see what you can do about applying the predicates, any other predicates you have in your and, to things that don't end up matching the index. So what does the most selective access path mean? It basically could mean cutting down the most on tuples, or it could mean the thing that is going to require the fewest IOs to be able to compute. Okay, so terms that match the index, it says you don't have to bother dealing with tuples that fail this. The index avoids irrelevance. The things that satisfy the index satisfy the index. So whatever predicates match the index, you know that you're okay. And you still have to go ahead and check the other stuff out, but you may have to, actually get the data to do it. I will remind you that, as we've already discussed, you can do index intersection. So you don't have to just use one index. You can do TID intersection, where you use two different indexes and you only retrieve the tuples that satisfy both. So if you have an index on date and you have an index on BID, and you have a predicate that tells you, TID less than that and BID equals that, you can use both indexes to restrict what you actually retrieve rather than just a single index. So here we have day and BID and SID. If you have a B-tree index on day, you could use that, and then you'd have to check BID and SID to be able to figure things out. If you have a hash index on BID and SID, then you can use that to be able to only get the things with BID 5 and SID 3 because you have equality there, and then you have to check out the date. But as I mentioned, if you have both of those, you can do index intersection and only retrieve the data that satisfies both, if you have both access paths. Question?
Sorry, what did you mean by then apply any remaining terms that don't match the index?
Well, let's again look at this example. Suppose that my index is on day, then what I can do is use the V-tree index to only get the things with days less than August 9th, 1994.
Right.
But if that's the index that I'm using, I still have this conjunction that says BID equals 5 and SID equals 3. I still have to check that. Those are the remaining terms that have to be checked. In the same way, if I just have the hash index on BID SID, then I can only retrieve just the data that corresponds to BID 5 and SID 3. But that doesn't help me with my day predicate. I retrieve the tuples and I have to check that the day is right. On the other hand, if I have both of these indexes, I can do index intersection or RID. I sometimes will say TID for tuple ID, but we'll mostly say RID in this class. If I forget, remind me, but I will often say TID or TID instead of RID or RID, just out of old habits. But synonyms, so you got the idea, okay? And you can intersect multiple things. Of course, it's the cost of having to do that intersection. So here's a query that we're going to deal with. Now, for our purposes, again, I told you I was simplifying 4K to be 4K instead of 4,9096. For our purposes, we're going to assume that there are 20 letters in the alphabet. Sorry, Wayne. Sorry, UVWXYZ. We're not going to deal with you. Okay, we have a 20-letter alphabet. Could have picked a language that only had a 20-letter alphabet, but we'll go with English. But UVWXYZ, not important.
We need some.
Okay, so we're going to be doing a selection from reserves where the relation name is the name of the reservation, the R name. I forget whether I called it name or R name, but here I'm going to call it R name for a reservation name, is less than C, which is to say the reservation name has to start with A or B. What did I mention? Only 20 letters in the alphabet? We're going to make another very simplified assumption, which is that the reservations are uniformly distributed across my 20-letter alphabet. Same number of reservations. It's a randomly generated reservation name. It's equally probable we'll start with A or B. We're only dealing with capitals. A, B, C, D, all the way up to T. No UVWXYZ. So basically saying that the reservation name is less than C, so 2/20ths of the reservations will have letter less than C, which is 1/10. Okay, so the cost of finding the things that qualify, if I'm using an index, it's going to depend on the number of tuples that qualify, how many things start with either A or B, and if I'm using my index, is it a clustered index or a non-clustered or unclustered index? Non-clustered or unclustered synonyms. So basically, I have to be able to find the data entries using the index that correspond to the predicate. And again, the indexes, particularly if the top layers of the index are in memory, the cost of using the index probably won't be that expensive, particularly, they're going to be consecutive. I mean, the whole point of the index is the data entries corresponding to values are consecutive, whether it's a clustered or a non-clustered index, right? You just look at the leaves of the tree, which are chained together. And then you actually have to get the records. We know that with a clustered index, getting the records can be relatively cheap. If the data is memory, the cost is going to be relatively cheap. These days, again, a lot of the data is in memory. But if you have a non-clustered index and the data is not in memory, then things can be more expensive. Of course, we do have that sorting by page ID trick that we've talked about. Anyway, if we assume uniform distribution of our names, which is to say the same number of names start with B, start with E, start with, L, start with T, nothing starts with W, that's, last 6 letters have been thrown out, then 10% of the tuples, that is 2/20ths, are gonna qualify. Because there are 2 letters, A and B, everything starts with AB, or up through W, 2/20ths, up through T rather. 2/20ths of the things are gonna qualify, so it's gonna be 1/10 of the tuples. So what is 1/10 of the tuples? That would be, you may remember that we had, in reserves, we had 1,000 pages, and we had 100,000 tuples. So the answer to the query, the result, is gonna be 100 pages worth, and it's gonna be, which is 1/10 of 1,000. And it's gonna be, 10% of the 100,000 tuples, which is, 10,000 tuples. Now, that doesn't mean that I'm only touching 100 pages. That's what the size of the answer is. I may have to touch a lot of pages to get that answer, but the answer is gonna be 1/10 of the tuples. So with a clustered index, then the cost is gonna be about 100 pages. Because I'll be able to get the things inside my index and my data, and if basically it's just gonna be the 100 pages that I need. Because the data is there in the index, it's consecutive. With an unclustered index, I might have to, since I need 10,000 tuples, and unless things are cached, I might have to each time read in a page that gets the tuple if my page is not in memory. Again, I have this sorting based on page ID trick. Each tuple might require a page access. Again, this is a simplified assumption that data isn't cached, or that I'm gonna be unlucky and never find the tuple that I'm looking for. Again, with large name memories, these are unreasonable assumptions, but we're talking about what goes on in this stuff. Let's look at an operation that we've spent a lot of time on in 180, which is removing duplicates. Suppose that I want to look at reserves, and I want to look at the different values of SID and BID. Recall that reserves has a key which is SID, BID, and day. So I want to be able to get the distinct values, and they're not there. And the relational algebra operation projection, regarded as a set operation, removes duplicates. Right? But SQL systems, when you have a select, if I didn't say distinct, SQL has a couple of really good reasons why it doesn't remove duplicates when you just say select. Reason number 1, it's a lot of work. Reason number 2, it would be wrong for a lot of queries, and we talked about this in 180. If I'm trying to find the average of the stocks on the New York Stock Exchange, it matters whether I have 100 stocks that are priced at $10 or only one that's priced at $10. That affects the average. Getting rid of duplicates would give me the wrong answer. So basically, SQL systems don't end up removing duplicates unless there is the word distinct there. They tend to be lazy about removing duplicates. They deal with it, sometimes they deal with it early, sometimes they deal with it late. This is an operation. It's not one of Codd's operations. He hated duplicates. But it is an operation that has to be preserved, executed at some point if the query is asking you to get rid of duplicates, and they're not already eliminated. So again, it's sets versus bags, multi-sets, etc. Here are 2 approaches to get rid of duplicates if you need to do it. The obvious one is sort. And what you do is you do a sort, and as you get multiple things of the same value, you don't keep them around and then get rid of them at the end. You get rid of them when you find the same value multiple